Okay, so this is a first talk of a two-part series, like super fast. So it's a little bit different from the previous talks in today because I'm going to kind of use their machinery but not really talk about the actual machinery. It's going to be kind of like an application that I personally care a lot about, and that's transverse links. So just for an overview, so this is part one. It's going to be the geometry point of view, and then in the next talk I'm going to talk about the combinatorial point of view. So for the geometry portion, the main resource is an EENS paper, and the key word here is filtrations. So if you Google that, maybe that will just show up. First I'm going to tell you about transverse knots. So really all of this stuff works for transverse links as well, and I'll tell you what those are. But for simplicity, let's just focus on knots. The theory is like mostly similar. Okay, and then to get a sense of what's happening when I build this filtration, I'm going to first verbally tell you the overview, and then we'll talk about, in general, how do you get filtrations from hypersurfaces. And then actually the filtration on the DGA. Okay, so first of all, maybe not everyone here has seen transverse knots or like thought a lot about them. Let's first talk about what they are. So for concreteness, let me just work in the setting R3 with the standard contact structure. And for the sake of like being really concrete in your mind, let's think about this as being the rotationally symmetric tight contact structure. So, you know, contactomorphic to standard contact structure, whichever one you're thinking about. If you care, I'm thinking of R3 as points x1, x2, x3 because I want to reserve the variable z for later when I go into 5 dimensions. Minus x. You know what? It doesn't matter. It's going to be symmetric, or maybe the orientation is backwards.
That's good.
Okay. Yeah, it's rotationally symmetric. You got that picture. Okay, so if you have a knot inside this contact structure, or contact manifold, such that all of, like, if you think about every single contact plane here, the knot is going straight through it transversely, then it's a transverse knot. So if you really wanted to write that down, this is transverse if, you know, for all your points x in your manifold, your contact form, which is global in this case, sorry, it's not equal to 0, because it's going straight through the contact planes. Okay, is everyone okay with that? So for some context, you know, we've been talking about Legendrian knots. So you can imagine when the knot is always tangent to the contact plane, this Legendrian. Somehow, if you lose some information, you're going to take some equivalence classes. So transverse knots are going to be equivalence classes of Legendrian knots. So you can imagine if you ever have any Legendrian knot, you just push it off kind of transversely from the contact plane, and the contact plane would have changed in that direction, so you get a transverse knot. It's kind of more generic to be transverse than to be Legendrian. And finally, you can go to smooth knots. So like maybe equivalence relations and equivalence relations. Okay, so just as we said that for Legendrian knots you have this notion of some knots are like Legendrian simple or not simple, you still have that same phenomenon. There's still like botany going on. Or, yeah. There are knot types with different transverse knot representatives that are not transversely isotopic. And I didn't tell you what that was, but maybe that's self-explanatory. You know, you go through an isotopy and they're always transverse. Okay. So transverse knots have some classical invariance. Oof, okay. So classical invariants. So let's just say there's two of them. There's the actual like smooth knot type. And then there's this thing called the self-linking number. I'll write that down. Okay, so if you're given K as the closure of a braid, there's an easy formula for this. So let's say if I have K is equal to, you have some braid, you close it up. If B is in Bn, then n is the braid index, right? And rise of this braid is going to be equal to the number of positive crossings minus the number of negative crossings. Okay, so the easy formula is just equal to if K is equal to the braid closure, then your formula would just be, let me get this backwards, rise minus the braid index. And if you check it like, well, I'll talk about this later. Anyways, so if you want to think about this geometrically, think about your braid closure and then just pick a ciphered surface. Okay, so the self-linking number is basically like the relative twisting between like the ciphered surface and the contact structure. So if you want to hear more about that, I can tell you that, I don't know. But for our purposes.
Why does a braid give rise to a transverse knot?
Yes, I will talk about that in the next talk. So I guess the general idea is like,
it's okay, talk about the next talk.
I'll just do a 30-second thing. It's like, so first of all, would you agree that any closed braid will give you a transverse knot? Because if you think about the standard rotationally symmetric one and you go way out into infinity, the planes are going to be basically vertical, right? So if you just like pick some very, very, very close to the XY plane and draw your braid, it's going to be transverse. Now the other way is like a deep theorem. That's going to be like Benneken's theorem, but I'll note that later. Yeah. Okay, so a really interesting thing is that finding effective transverse invariance has been really hard. So effective just means, distinguishes knots or links beyond just the classical invariance. And to my knowledge, there are only two kind of like families, two types of transverse knot invariants that are effective, or known to be effective right now. Okay, so here's my list. Right, so the first one I knew about was this one from Knopfler. Basically, you just like have this contact element, then you take some equivalence class thing, and you get this element. This is not a Hager-Floor conference, so, but it's effective. And the second one is just the invariant we're talking about today. I'm just going to write star. This is transverse knot contact homology, or like, the algebra, DGA type. The reason why I say family is because this comes in many flavors. Like once you have one really big invariant, you can take pieces of it and, it's still a transverse invariant. So star can equal either the minus theory, or there's a hat version, double hat version. These are easier to compute. This is kind of the one we're going to define. It's like the grandfather of all these. Okay. Ooh, I thought I was going to be able to explain my excitement in 5 minutes. Okay, so I'm really excited about this because for like a couple years of my life, I've been staring at this invariant from Kavanagh homology, if you guys care, and like nobody knows if it's effective. So I only know of these two. So it seems like the fact that Lenny was able to prove that, for example, here's an application. Here's a smooth knot type. If you only compute the degree 0 portion of this algebra for two particular transverse representatives in here, you can, compute the core algebra portion and then, augmentation polynomial stuff, which we didn't talk about, but you compute a number and you get different numbers. And then you prove that if you get two different numbers, you're going to have not isotopic knots, or really the converse, or the contraposited.
Excuse me.
Yeah.
Just to check my understanding. Effective means not contained in these two, smooth type and self-linking, right?
Right, so these will have the same self-linking and smooth knot type. So smooth knot type, and then they have the same self-linking. But they are not transversely isotopic. And I don't remember if this is a good example of this, but there are definitely knots, transverse knots, that have the same smooth type self-linking number and this transverse invariant. So previously we just didn't know if they were the same or not. So there are many examples of this.
And you just remarked that this psi invariant from Havana homology is not known to be effective or non-effective.
We don't know if it's effective or not. It's not effective for like smooth knot types up to like 9 crossings or something. Like if you compute it all.
Okay.
So we really don't know.
At some point we thought we had a proof that it was not effective, but it turned out it was because we didn't understand spectral sequences.
Oh.
It was sad.
So since I don't understand spectral sequences, I think I can prove.
Good.
Yeah. Okay, so now I didn't realize how slow I'd be, but maybe I'll just make it really, really condensed. So let's go for the overview. And maybe I'll just draw pictures. So remember, we're in this contact structure. Let me just warn you, because this is important. I'm talking about two different contact structures here. So contact manifolds here. There's a 3-dimensional one, right? So there's R3, and there's the standard contact structure. And in here lives our transverse knot K. This is what used to be the smooth knot. But remember, now we're still doing like Legendrian contact homology. So there's a second 5-dimensional contact manifold, right? There's ST star R3. I'm just going to write kernel of what, like D, Z minus lambda canonical. So lambda canonical is, technically this is not correct, right? This is really, we're viewing it as the one jet space, which is T star S2 cross R. We've seen this picture like so many times today. So this is the coordinate Z, and don't get it confused with X3 over here. They're two different contact manifolds, and they're two different dimensions. Okay, so in here, element, no. We have our conormal torus. So the idea of this filtration is that we're going to look at this conormal torus inside this 5-dimensional contact manifold. And then also in this manifold, we're going to construct a pair of 3-dimensional subsurfaces corresponding to a kind of like co-orientation of this contact structure. So this information turns into 3-dimensional spaces, and I'll draw a picture later, you'll understand it. And then, if we use the Lagrangian projection here, we're going to end up in here, right? So if you give this an almost complex structure, then you get to do a lot of cool things because you have so much more structure. Mostly, the most important thing is that if you have almost complex things intersecting, they're always positively intersecting. So what we're going to do is we're going to take the differentials for the Legendrian contact homology of this thing and intersect it with the projections of my 3-dimensional things, which are going to be complex hyperplanes. And because of positivity of intersection here, we're going to get a filtration on the differential. So the reason why I tell you this is because it might take you a while to stew it over, so that when I actually tell you, you will believe me more. I don't expect you to understand it right now. But does everyone kind of get the approach? Okay, and the significance of the transverse knot is that it's actually like a well-defined thing. Like this will be disjoint from my hypersurfaces that I'm defining. Okay, That's overview. Okay, so very briefly, so the main theorem, this is in the EENS paper, is that the stable tame isomorphism type of this invariant, so this differential will be filtered with respect to, intersections with these hypersurfaces that I'm defining, is a transverse invariant. So what does this tell me? Well, first of all, stable tame implies a quasi-isomorphism, so we also have homologies. Second of all, this construction is basically, like, I've seen it before in a different context. So maybe it's helpful to think about, if I have this sort of filtered complex, I can also get a lot of other invariants from it. So I took a survey of one person, and I think the most, you guys, maybe from the survey of one person, the easiest way to understand like a filtered complex is thinking about just like the spectral sequence for a bicomplex, right? No? Yes. Okay. So the picture is, this thing is going to look something like, this algebraic picture, artist's rendition of this. So I said I'm intersecting with some sort of hypersurface. Let's call this like the number of intersections. Okay? And then this direction is going to be like the actual grading on my DGA. Okay, so this is DGA direction. So for each column, I'm going to add, I don't know if this makes any sense to, this is not a complex, which is why it's very much an artist's depiction of this. So normally if it looked like this, right? Now, instead I'm going to have a filtration due to like the number of intersections. So maybe if this differential originally had a disk that actually does intersect my hypersurface once positively, then it's going to go to a bigger power along the intersections axis. So naturally you'd expect this thing to really be, so this is a DGA over the coefficient ring z lambda plus minus, mu plus minus, adjoined. It's going to be like two different hypersurfaces. So technically there's like another dimension. Okay, I'm not sure if this confused you guys more. Are there any questions? Okay. The reason why I wanted to draw this is whenever you have this kind of picture, well, first of all, I can set u and v equal to various things, and that'll give me my hat and double hat theories, which maybe I'll talk about in the next talk more. The other thing I can do is actually reflect all of these things, right? So instead of just taking like a one-sided infinite number of copies of this thing, I can try to invert these variables. So then these dots will kind of continue to the left. So I'll just have this like symmetric complex going this way, also going this way. And turns out that gives you an infinity version of this, which turns out to actually be a smooth invariant.
But, do you have some kind of positivity of intersections or something, which would
Yeah.
prove that your intersections with the hypersurfaces are always a positive count?
Right, so it turns out, first of all, your disks to the differential are pseudo-holomorphic, right?
Mm-hmm.
And then these hypersurfaces that I really probably should have defined first are complex, almost complex hypersurfaces. So you do have positive intersections, which is why the arrows never go backwards, they always go this way. Yeah. So in this sense, it's a filtration. Okay, so any other questions? Okay, so now what you've been dying to know about is, what is this hypersurface? Oh yeah, I forgot to say this at the beginning. I typed up these notes and put them online, but I didn't draw the pictures, or I sent them to people. So if you're going to get anything out of this, get the pictures. and then look up the words later. So, okay. So, all right, so let's just briefly talk about how to get filtrations in general from hypersurfaces. So I'm still thinking about this not contact EGA, but I'm just gonna say like for any old hypersurface with certain properties. So remember again, we're here, and we have already chosen this almost complex structure. If you have a hypersurface, which in this case is really just a real surface, that is in here, that's almost complex, and it doesn't actually intersect the projection of your Legendrian conormal torus, then it makes sense to actually think about disks in the differential intersecting with this hypersurface, right? You can use a formal variable u sub, I don't know, h bar to record intersections. And I think I keep saying this, and it's not really clear until I actually write down what the new differential looks like. Okay, so if you have a filtration, a filtered differential, all I'm going to do is change the original differential. In the interest of time, this is things you can count. And you know, like some signs and stuff. And then, normally we would have had like just this. Okay, maybe I need like some u in moduli space a to b vector for context. Okay, right? Things you can count. But here instead, I'm going to put in this formal variable u sub h bar and the number of intersections that my disk has with my complex hypersurface. And we established that this gives you a differential. And then there's this, this really just has to do with the framing. So A, remember, is in H1 of my conormal torus, which is generated by some meridian and longitude. I might as well just pick like the standard ones. This is a nice symbol that means if A is equal to like this many meridians plus this many longitudes, like the standard one, then exactly what you think exponentiation means. E to the A just means mu to the m times lambda to the L. So it's just symbols. Okay. So now I'm actually going to tell you what the hypersurface is. Probably via picture. Okay, so let's start by defining my three manifolds, right? Defining H plus and H minus inside ST star R3. I'm working in here because it's easier to explain in here, but you're gonna have to like, you know, take a contactomorphism over. Okay, so I was told blue erases. So imagine you're in R3 and you have some point X. So here there's a contact plane, and since our contact structure is global, we have a co-orientation. So pick a co-orientation. That gives you a plus side and a minus side. So let's say this is a plus side. Okay. So in this picture, I'm going to use a flat metric to identify, you know, T, X star, R3, and T, X, R3. Okay, but I'll tell you which one's which. So the contact plane is in here. The point is just in the here. So if you use the flat metric and you see this perpendicular covector, and then also this perpendicular covector of length 1. Let's call this one like v plus and this is v minus. Okay. So maybe just thinking about it in the tangent bundle, if you vary over x, then all the v pluses are going to vary smoothly, so you're going to get a 3-manifold worth of v pluses. Is that okay with that group? Okay. Same thing with the v minuses. Okay, so except that instead of doing that in here, my actual h plus and h minus are going to be in, their unit lengths, they're going to be in here, but they're actually going to be covectors. Okay, so basically I'm going to take, like, h plus is, you take all of your v plus duals. But what really is v plus dual, right? So if I'm thinking of v plus dual is, some notation, it's really like pairing v plus like this, then what is the kernel of this covector? It's really just this contact plane, right? So this covector is really just alpha sub, or alpha of x, and then it technically like eats a vector, but we just think of it as the covector.
You have to normalize it, right?
Yeah, that's why I wrote ones.
So it's alpha of x over the length.
Yeah, okay.
Yeah.
Okay, so everything's in here. Thank you. Yeah, so if you actually want a definition of what that is, so just for your future reference, the notation will look like this. R plus or minus times some vector v are the points in, this R3 is just some vector space, by the way. X has to be a positive multiple for plus, and then minus is a negative multiple. So I'm sorry I cobbled these two definitions together. H plus would be the points x, y, now actually in my 5-dimensional contact manifold. Y has to be in R plus dot alpha of x. And then in the interest of time, similarly for H minus. Okay, so unpacking this again, normally you would think of, this set of vectors as, this set of vectors as just all of these, but since we're normalizing, we only get one. Okay, so everyone believe me, that's 3-dimensional manifold thing. Okay. So when K is transverse, remember it's transverse because it has some relationship with alpha, right? What you really have is, here's your contact plane. K is doing some transverse thing. Your normalized alpha covector thing is pointing some direction such that when K is not flat against this. So if you look at the part of the conormal torus as being like a bundle over K, right, that one circle is going to be kind of, perpendicular to the tangent vector of K or whatever. In any case, since K is transverse, this circle is not going to contain this point. So that's the whole point why you can do this. It's in particular for transverse knots because of this. Okay, when K is transverse, we actually have that this, really the projection intersect, just kidding, we're not there yet. Intersect this or this is equal to empty set. Okay, So here's the hand wavy part. Claim, actually like, theorem of people. I'm not going to tell you why, which is why it's a claim. First of all, when you project it, well, you can do some finagling and choosing of contact structures on R3 that's still contactomorphic to our original one, and also some like finagling with like how this actually sits inside the entire cotangent bundle. A lot of this geometry to make sure that, I guess first of all, you can make choices. So that this will be true, but what does this really mean if I told you all these choices? Well, you're going to be able to choose H plus minus, both of them, such that it's invariant under the ray flow. And then when you take the Lagrangian projection, assuming, you will get something that's embedded. And then, so pi L of H plus minus are embedded. And also they are complex submanifolds for surfaces with respect to the almost complex structure. A lot of you look confused. Yeah.
Does making it invariant under ray, where the ray, can you see the ray flow in the original R3s, or?
No.
She does it, but
Yeah.
She doesn't.
So I guess you want to. Okay, there are representatives, and I can write one down, of the standard contact structure, such that you can both see the ray vector field as just being straight up, and also, well, it's just straight up, so it's geodesic in R3 with a flat metric. And that corresponds to kind of the projection. So like if you have this thing in that contact manifold and it doesn't look any different when you translate up and down, then when you squash it, you still get it embedded. And it's still like, okay, maybe that's not clear, but it's embedded. And this is like pages and pages of finagling, which I'm probably not doing justice to.
So I think it's also possible to actually draw this quite explicitly over the sphere, over the two sphere inside jet space, right? By drawing some kind of non-Lagrangian section there. But okay. It's,
Oh, you mean like actually draw an example?
yeah, or maybe it's not precisely that thing, but it's going to be close enough. So there is a, we all know how to draw Lagrangian sections inside cosine bubbles, but it's also exactly also possible to draw homomorphic sections inside cosine bubbles, right? Or kind of symplectic sections. But
yeah.
that's just a remark.
Yes. I have thought about this, but you're taking like sort of a four-dimensional intersection, but you're taking the whole picture down to 2 dimensions to draw it, right? So
you can kind of make the section, two sections, say, over the north hemisphere and south hemisphere of this two sphere.
Mhm.
And it will not be df, but it will be something like df precomposed with I or something like that. Or some Duracell harmonic function. Anyway.
Okay, yeah, so I haven't been able to like imagine.
It's a section, and it's not a closed one form. It's a primitive or symplectic form. It's a section being a legal form. No, I'm just describing these hypersurfaces inside cosine formation. That's graphs. But graphs over legal forms, not graphs over closed forms. Legal forms in the function.
Okay, so to finish up,
Melissa, why don't we say you don't have to rush to this, you can start with this after tea if you want.
Don't I still have 2
Oh, you
minutes?
still have a couple minutes.
I have this much left.
Oh, okay.
I've been timing it. I've been trying to time it really well. Okay, so finally, the theorem is that, the whole point of this talk was to define what this is. So here it is. Okay, so you're going to have the same generators as KCA, except remember we're working over, we have these variables U and V kind of recording how much we're intersecting with this H plus and H minus, which I didn't technically write down, but I alluded to many times. So we're actually tensoring by this, which forever I'm going to call R now. So there's technically like a 2-dimensional lattice worth of all of these generators. And the boundary. Okay, stuff you can count. So, it's still U in this moduli space. It's 1 sine of U. And then now you're taking U, counting the number of intersections with your projected, like Lagrangian projected plus. So I'm using the bar notation to be like pi L of H plus, which might have been a subscript previously, yes. Of, unfortunately, little u times V, counting the number of intersections with the negative co-orientation hypersurface. And then you still have your lambda to the L, mu to the M. And it's a filtration with respect to the power of this and also the power of this. So it's doubly filtered. Okay, that's all.
Are there questions for Melissa?
So what kind of computable invariance do you get out of this? Do you look at the associated graded? Do you look at
Kind of. You don't have to do all of the associated graded, just like the 0 portion. So in the next talk, the combinatorial version, Lenny has a program, transverse.m, Mathematica. Basically, from this you get like a 3-variable augmentation polynomial, and then you can plug in, various numbers, and then tell a computer to compute this polynomial. And if you're lucky enough, you can find that one transverse invariant, like some braid representative, right? And then give it another braid representative for the same smooth knot type, and you get 2 different values. Then you have distinguished the 2 transverse knots. Yeah.
So what was the Q variable in terms of these? I believe it can be expressed, but what was it? Maybe this is later, I'm not sure.
The Q?
The Q variable from this.
I don't think there was a Q.
No, there's a Q. It's U was renamed Q at some point because the physicist amended it.
U is Q.
So
Okay.
if you localize by inverting U as well, so you can set V equals 1. Actually, the U and V, once you localize, they are no longer independent. So you might as well just set one of them equal to 1, set V equals 1, and then localize at U, so allow inverses of U, and then replace the letter U by the letter Q, and that's
Okay.
I mean, geometrically it makes sense because the time you're counting the number of times you're passing through the wall, so you're counting the relative classes. That's what you're doing.
If you forget about positivity of intersection, then counting number of intersections is just calculating the relative homology.
Did Laura have a question?
My question was answered. I was just wondering why I keep track of both the positive and negative H. Like if you,
Oh.
but
Yay.
the answer is
I wouldn't have been
that's
able
a
to.
choice that you don't have to. Like one makes.
Oh, yeah. So the hat version is actually set one of them equal to 0, one of them equals 1, and there's an isomorphism between you. Yeah.
You don't get some transverse
Okay, let's thank Melissa again. And the next talk will be at 4.